Welcome back to Sustainable River Basin Management, Part 5, our last one of Module 2. And today we'll be continuing on nutrient cycles and planetary systems boundaries. We've last time talked about soil fertility and the effect of our breaching of nutrients from the terrestrial to the aquatic system, the effect of the marine dead zones. I just want to show you a few other examples of nutrient fluxes from rivers to the sea, as to show you the long-term effects of it. This is an example from the European Environmental Agency. It shows us years here and nitrogen loads along here, and the different color lines here are measurements of nutrient fluxes from rivers into the Arctic Ocean, into the Baltic Sea, into the Black Sea, the Celtic Sea, the North Sea, and the Mediterranean Sea. What you can see is that major efforts have taken place to reduce that nutrient flux from rivers into these seas. It has reduced substantially. We have the Arctic Sea here as a sort of a reference line here against which we can measure other the nutrient fluxes in other parts of the world. What we also see is that there are quite some ups and downs in these amounts of nutrient loads, and very often we can link those to specific events like major disasters or major even political changes or major implementation of or enforcement of laws and regulations. So we can link this, although we don't have countries named here, but we know which countries are bordering or these seas, or which rivers pass, ending or draining into these seas, pass through which countries. So this is quite interesting to see that although there are major efforts done on reducing those loads, still they are substantial and still they are very susceptible to specific non-action or actions in certain parts of the river system, and still being detectable in those seas. So there's a long-term effect in this, notable from an overall perspective of what individuals can do, what politics can do, and how long-lasting also political interventions and scientific interventions have to be to produce measurable effects. Another example here, which gives us a good sense of the nitrogen load from continents to oceans, as a nutrient leakage from agriculture and from sewage. We have here a global map which shows us on one hand in colors the global change in dissolved inorganic nutrients. We have blue here, a negative reduction, and in red the extreme increase of nutrient loads. You can see which parts of our terrestrial zones are have seen these major increases. Also Europe has put a lot of effort into changing, enforcing changes in the agricultural sector. Still, there's a major increase in nutrient loads, the same in the Asian region here. Now, what is a good indicator for sewage and nutrient leakage from the continents to the ocean are mud flats. Mud flats are the waters along the shelves of between our continents and the ocean. Our mud flat numbers, or the black dots here, have increased substantially over the years, although we know that our sewage treatment facilities are in place, and we try to do our best to capture and treat water before it's been released into an ocean or into a stream. Still, it's been detectable and on the increase. Whereas our more natural marsh systems have been substantially decreasing, and we are still on the decrease. So those are measurable indicators for these nutrient loads, which in itself can build up an index towards monitoring our planetary boundaries. Now let's move out of this basics and look into our global nutrient cycles. Now, our nutrient leakage means, as such, a leakage is not a loss of nutrients from one ecosystem. It's a cycle. What has been removed from one ecosystem means that it's been moved out of one ecosystem into another ecosystem. So one is a losing ecosystem or a storage compartment, and another is a gaining nutrients. Whether it is useful for that ecosystem or not is not been said here. So the law of conservation of matter applies also on when we talk about nutrients and nutrient cycles. So nothing will simply disappear somewhere. It will always appear in another part of our cycle, in another form, and eventually come back to us. So what we have been doing is breaching ecosystems, and what the result of this is that we have to look not only at managing our landscapes, but to look into what happens at the transitions, at the fringes or landscape boundaries. And we also have to look into the matter as not something that can be influenced at a local scale, but it has a global impact. So we can do our interventions at local scale, and still globally it will not be picked up, or we may change something locally and it will have its influence at different locations globally due to the linkage in cycles. Now let's look into the most important cycles, and let's start with the nitrogen cycle here. I've loaded those complete figures out of this report here, which I really recommend you to read in detail to understand it properly. The Millennium Ecosystem Assessment of 2005. What we see here are the storage compartments, those boxes here, different boxes, and the division into our oceanic part, the ocean water part, the river systems here, and our terrestrial part above surface and in rocks, soils, or geological formations. And we have our atmosphere here. In all of the other images which I am going to show you, it will always be the same concept. And the black arrows are indicating our fluxes, our flows between compartments, and the black arrows will show us what the natural system has been and looks like without human intervention. So what we see in the case of the nitrogen cycle are essentially two major cycles. One involving the ocean and one involving our terrestrial surface, both essentially linked to the atmosphere and in minor quantities to our river systems. Why nitrogen is so important? It stimulates primary productivity, and it is easily being washed out of soil systems or from soil surfaces. Will not be taken up and be washed out or fixed in or washed into the groundwater systems and reaching the groundwater tables. So the processes which take place is that nitrogen changes from its atmospheric, from its gaseous form to nitrification and ammonification, denitrification process back into nitrogen. So there are microorganisms and plants adapted to changing the state in which nitrogen occurs. There are microorganisms and plants able to take up nitrogen from a gaseous environment or from an aquatic environment and fix it or put it into a solid state in plant growth or in non-biotic matter. So in theory, as we increase, we could increase our plant activity in this way. So a different cycle on this is a completely different cycle compared to this nitrogen cycle, where we have microorganisms adjusted to working and removing the nitrogen from current state. Is the phosphorus cycle. We have again our ocean compartment here. We have the atmosphere here, and we have our terrestrial compartment here. And what we can see here is that we essentially have a minor cycle occurring between our terrestrial processes, our terrestrial compartments, which have very little connection with our our terrestrial aquatic systems, and even less of connection to our oceans. So, and there's basically no very minor portion of the phosphorus ever reaching the atmosphere. This is the natural, and we have changed this. The gray arrows indicate the flows that were a result of our human intervention. We have been removing phosphate from minerals, from our geological storages, and put this into an additional cycle that to increase our agricultural production. So there's an industrial production of it, which has increased the amount in soils, and it has also influenced the amount of or doubled the amount of phosphorus which is washed into our river systems, and which eventually will reach our oceans again and influence aquatic growth within our oceans. Now, what this means is that very little phosphate has been taken out by natural processes, by weathering processes out of our geological reservoirs. So phosphorus is one of the least biologically available, however, major nutrient. And what we have observed is by adding phosphorus to aquatic systems, rivers and oceans, they respond with a lot of biological activity, which is by far larger than by adding nitrogen to aquatic systems. So phosphorus is one of the limiting and driving nutrients in aquatic systems. However, it played a minor role up to the point when we started mining and adding phosphorus to our as part of our fertilizers. So phosphorus is also usually not transported in an absorbed way on soil particles. It requires, it's not in solution. It forms large colloids or large molecules, hydrous particles, or it gets absorbed on soil particles, and only in that way it is being transported. So it becomes a major component out of soil or sheet erosion, soil erosion, desertification processes, washout from land surfaces due to storm water events, and for that reason increases from agricultural fields a washout into our aquatic systems. So what phosphorus used to do, has been moving in geological time scales, and we accelerated it by the way how we use our land water systems. Now let's look into the sulfur cycle. It's also a very interesting one, where we have a major storage compartment in the atmosphere. We have a very active linkage or a very active cycle between the ocean, our aquatic ocean system, and the atmosphere, and we have only minor connection between the terrestrial system and via the terrestrial system to the ocean. So this is what it used to be without our human intervention, and this changed substantially by us releasing sulfur into the atmosphere by burning fossil fuels, by mining coal and using causing fires and dusts, and this has created an additional cycle that now originates from the terrestrials, from the land surfaces, and contributes to the atmospheric compartment. And by that, the major deposition again occurs over the oceans, and substantial deposition also takes place over the land surfaces again. Now, what the impact is, or what it means, sulfate forms a crystalline aerosol. The way this occurs in the atmosphere is as an aerosol, in many cases as a crystalline, and it's in crystalline form, and it is a very powerful actor for cloud condensation. So while this may be useful in situations where rainfall has been evaded for, we could think of using this as a mechanism to generate clouds and to generate rainfall over a certain area. However, these sulfates dissolve in rainwater and form a sulfuric acid, and that is a strong acid in itself, which reduces the pH in rainfall, in rainwater, which then reaches the surface. Now, this coming diluted in rainwater and being deposited on our Earth's surface in wet form, first of all, and later also in dust or in dry form, has major impacts on plant life, on photosynthesis. Remember the dead forests that were observed over large parts of Europe, large parts of the United States, as a result of the deposition of acid rains. It also leaches the soils, and by that reduces the buffering capacity of these soils. It has an impact on our constructions, on buildings. Buildings get damaged. You may be aware of the case of the Taj Mahal, and industries were stopped to operate in this area to reduce the amount of damage and due to acid rains, although this is only local, and you see this as a global cycle. So what happens locally is only a minor impact factor compared to what the surrounding areas, neighboring countries and so on are doing. It leaches the soil, and it reaches the point where soil buffering capacity will be taken off. So the effect is that we have an acidification of our ocean, which has a very negative impact on our aquatic lives in oceans again. And now lastly, I want to briefly talk about the carbon cycle, and the best explanation you may find in one of these two reports here. And again, we look at first the natural carbon cycle, which is a triangle between soil and plants on our terrestrial surface, on our land surface, linking to our atmosphere as one of the compartments, and linking those two to our oceans as a major storage for carbon. This is our natural cycle, and the major transportation pathway is from our terrestrial activities on the surface of our land to the atmosphere and then into the ocean. So any of the weathering processes or any of the geological storage compartments have not played any role as the groundwater or the river systems have not played any role in this carbon cycle from a natural point of view. It's only minor what has been washed out or transported in rivers or weathered. Now, we know that the carbon cycle has been changed substantially by human perturbation, and nowadays it looks very different. We still have our atmosphere as a compartment, we have our oceans as a major compartment, and we have our land. However, here we are not differentiating between what happens on the surface anymore, because what happens on our land surface has become a minor component of the carbon cycle. The major component or major storage and input source are our geological reservoirs. We have been mining our fossil organic carbon, our gas, our oil, our coal deposits on one hand side, but not to forget also our rock carbonates, which we use for construction, for instance, for cement, for any large dam, for instance, any large urban area. The rock carbonates have become very important. So this is an additional, we have formed or caused an additional cycle which in itself is feeding back into our oceans. Now, what happens in our oceans? We have the oceans as our major sink for carbon sequestration. The plant synthesis, photosynthesis plays a minor role, although there may be forest encroachment being observed, which could be a response to more carbon dioxide availability in the atmosphere. But the major sink or major storage for this additional released carbon dioxide are our oceans, which, thinking about our carbon system in aquatic environments, increases the acidity of our oceans. In itself, it reduces the amount of organic life based on carbonate structures. It destroys it. Essentially, it reduces the biodiversity. At the same time, due to our global warming, we reduce the amount of carbon dioxide that can be stored in a warmer ocean storage. So at the same time, we see a release of carbon dioxide from the oceans due to an increase of the temperature of our oceans. So those are the major changes that we can see and are measurable, and which all in themselves are quite worrying to our own survival and to the functioning, especially of our aquatic systems, of our river systems. At this point, I want to close our second module, and I want to suggest you two things. One, to read more about nutrient cycles. I could only touch it very superficially, but they are extremely important. You should check out applicable water quality guidelines. You should get water quality standards of your region. You should also get information about acidification of rain. Maybe there are pH measurements in rainfall and maps being produced regularly for your region. You should try to get that information and to improve your understanding of this. You should also, my suggestion is you should read about river restoration projects in your region. You may get information about what worked, what did not work, why did it not work properly, or what was successful and for that reason special. who was involved in it, who actually initiated it. Was it the local population, people that wanted it? Was it a politician? Was it someone else? Who actually drove it? Was it an NGO? Does it fulfill now the ecosystem services, and does it fulfill maybe all of the ecosystem services that we want from a functioning river system? And so on. You could think of more questions, and it's not a homework that I will ask you to present, but I want you to start searching about such issues and try to understand and learn more about that on your own. Thank you, and I see you next time for the next new module again.